Okay, the first atomic model that you need to know is J.J. Thomson's plum pudding. Okay, and the plum pudding is a sphere of positive throughout the whole atom. Okay, throughout that positive sphere is scattered particles which at this point we knew were electrons. Okay, so there's a sphere of positive with a scattered number of different negative charged particles called the electrons, enough so that it will balance the positive charge. Okay, they didn't necessarily know that there were physical particles that represented the positive. He just knew that, okay, an atom is made up of positive and negative. Okay, and the positive is everywhere in this sphere. But the negatives are actually small particles that can be moved from the atom, so they're scattered around randomly and they cancel out the positive charge, so they're neutral. Okay? The next one was Rutherford's nuclear model. Now, what you need to know about this model is how the experiment that he did basically gave them the results and made the observations they made that determined the nuclear model that they came up with. So what they did was they had a sheet of gold foil. Okay, they fired alpha particles, which we should know at this point are made up of 2 protons, 2 neutrons, also known as the helium nucleus. Fired those alpha particles at the gold foil. Okay. If this model, the plum pudding, was to be believed, then the expectation for firing alpha particles at gold foil, which should be made of a wall of those positive spheres with negative electrons dotted around, the expectation was that all alpha should pass through. Okay? The reason for that is because if you have a sphere that has the positive charge inside distributed everywhere, then actually the strength of that positive is quite weak at one point. Okay, so if you fire an alpha particle which is double positive at basically a foil of positive charges where the positive is spread out across the whole atom, it's not strong enough in one point to actually reflect the alpha. It should let it pass straight through. Okay, but then what was seen, some alpha did get through. Okay, but some alpha were deflected at different angles. Some alpha even reflected back. Okay. So when you see, hang on a minute, something is causing the alpha not to just be deflected slightly off course, it's also deflecting it backwards. The only way that this atom can reflect directly back and deflect the alpha particles is if the positive charge that is apparently everywhere in the atom is actually concentrated in a very, very small spot. Yeah? So otherwise, it should pass through because it's not strong enough. It's distributed, it's weak at a single point. If it's bouncing them back, it must be concentrated. So they said, right, concentration of positive charge is called the nucleus. Alright? All mass and positive charge is in that nucleus. Okay? Some did pass through though. And if you can, basically, if you can hit the positive charge head on and bounce back, then that's where all the positive is. But if you can also pass through without actually being deflected at all, there must be a lot of empty space. Okay? So there's also empty space in the atom according to Rutherford's model because of the fact that some did pass through. Yeah? All you need to know is this is the alpha scattering experiment that Rutherford did. What did he expect, first of all? Could be a 6-mark question, for example, or a quite big explain why this observation led him to believe that there was a nucleus. Expectation was all pass through because the positives should be distributed according to the plum pudding. Okay? Some did, but some were deflected at small angles, some were reflected back. All the positive must be concentrated, otherwise that wouldn't happen. But because some did pass through, there is empty space, but there's also a nucleus which contains all the positive that is part of J.J. Thomson's plum pudding. Okay? But what Rutherford also said was, there are also negative electrons in this atom, so they agreed on the fact that they were positive and negative. But Rutherford said electrons orbit the nucleus anywhere outside. Okay? So he said there is a cloud, if you want, of electrons, the negative particles, they're orbiting the outside of the nucleus, quite a big distance away as well. So the nucleus, he said, the size of the nucleus is roughly 10 to the minus 15 meters, but the whole atom itself is roughly 10 to the minus 10 meters. That means it is 100,000 times bigger than the nucleus itself, yeah? The whole atom. You may see different values. You might get 1.2 times 10 to the minus 10 meters. It doesn't really matter what that value is, but the order of magnitude, 10 to the minus 15 meters for the nucleus, 10 to the minus 10 meters for the atom, and I have seen one mark questions in the exam where they literally just said, tell me the relative size or approximate size of nucleus or atom. Okay? But he said they could orbit around the nucleus anywhere they wanted. Okay? In a cloud. Expanding on this, we have the Bohr model. Alright? And the evidence that supported the Bohr model, which was an extension of the Rutherford model, was this thing called an absorption spectrum. If you have the textbook, just have a look. This is basically red, orange, yellow, green, blue, indigo, violet. If you were looking at the spectrum of light, it would be a nice continuous spectrum of all the colours, red, orange, yellow, green, blue, indigo, violet, yeah? But if you pass this spectrum of light through a specific gas, for example, of a type of element, for example, neon, okay? And out the other side, you test what the spectrum looks like, you will get a spectrum with black lines. Now, those black lines on this spectrum represent the energies. Remember, red has the lowest energy, longest wavelength. Violet has the highest energy, shortest wavelength. Okay? If there is a black line here, then that specific energy has been absorbed by one of the electrons. Okay? This energy here is quite high, it's the highest one on this spectrum. That also was absorbed by the electrons. Very specific energies have been absorbed by the electrons. What's the model? Here's the nucleus. Here are the shells that we're now creating. Here's an electron on that shell. There's one on that one. If an electron absorbs energy, okay, generally the energy that the electron will absorb is electromagnetic. In this case, visible light specifically. Okay, so it's absorbing the energy from the electromagnetic spectrum, so waves. If it absorbs, if the EM wave comes in and the electron absorbs it, then it could jump to the next shell, right? It could move to a higher energy level. And then what happens generally is if it lands on this level, it's not being ionized, it didn't escape, it will actually drop back down. And in order to drop back down, it will emit exactly the same amount of energy as what was absorbed if it takes the same jump back down. Okay? What Niels Bohr was saying was, look, here's a black line there, and there for neon, for example. So the electrons in a neon atom have a very, very specific structure of shells. The electrons can only take that energy, that, and that. Yeah?
So each one has a specific amount of energy.
Exactly. Each one represents a jump that an electron can make in the atom between shells. It cannot take anything in here. If I did it again 1,000 times for neon and shine visible light through that cloud of neon gas, if you want, it will always be exactly the same. An absorption spectrum is almost like a fingerprint for an atom. If I showed you this again in 2 weeks' time and said, which element is this? You'd go, oh, I've seen those black lines in that exact place before, that's neon. If I took a different one, for example, I said, well, what about this? And it was like 2 lines only. Most likely, what could that be?
Red.
There are only 2 energy levels that this electron can absorb, this atom. Which atom has hardly any electrons? Hydrogen, okay? So the most basic spectrum is the hydrogen one, and it will always be exactly the same, okay? So what is Bohr saying? Rutherford said the electrons are in a cloud, they can go anywhere. What would you expect to see then? Well, in that case, if I shine light through neon, maybe one time there could be black lines there, another time there could be a black line there, it could be anything all the time. What Bohr said was, no, look, here's the absorption spectrum for the neon atom, and it can only take those specific energies. They're the black lines on my spectrum. If I do it again, you'll see the same, and again and again and again. Hydrogen will always be like that. So what his model was saying was, he agreed with the nucleus, he agreed that the positive charge was concentrated, nothing to do with that. He said electrons orbit in fixed shells. Okay? They cannot just go anywhere. They can't jump half a shell. They can't go from there to there. They can't take any energy they want. They can only take what is required to go from that shell to that shell. Okay? So that's the Bohr model. Plum pudding, improved by Rutherford because of the alpha scattering experiment. This is what was expected, this is what we've seen. So that was the model that was proposed. And then here, Bohr, no, they can only orbit in fixed shells. If they absorb, they jump. If they drop, they emit. Here is the evidence, your absorption spectrum. Okay? If an electron gains enough energy that it doesn't just jump to the next shell, it actually leaves the atom. That is called ionization. If you ionize an atom, you've lost an electron. That particle can go on and cause ionization elsewhere. You're left with a positive ion, and hence it's called ionization. Okay? And they're the three models. Luther, if you pause it there, and I can just post them up in 6A, these, that was basically 6.